That's my cue. I always listen for that recording in progress voice, and that tells me that it's time to go. Hi, everybody. Welcome to the virtual night sky, our presentation for, goodness sakes, we've made it to August the 24th. Summer's winding to an end. The monsoons are still strong, but winding to an end. But most importantly, in our world, where we're from, school started. ASU classes began last Thursday, and we have a record number of students on the Tempe campus. I think if I remember the numbers right, I think they said it's 74,000 students started. That's the size of a small city. In fact, ASU, I don't know if you know this, is essentially by population the size of Yuma, Arizona. So there it is, about 3 square miles, right, nested in the middle of our city in Tempe, and it's a city within itself. So there's lots of excitement, lots of energy, lots of little sort of, finding your way around. The fall is also especially good because that's when we get all our new incoming freshmen. Ones that are sort of like they haven't exactly figured out what university life is like, but we're there to kind of help them do that. So it's great to see it happening. And after the COVID years, it really is great to see that many people come show up and be part of our school. Tonight, we're concentrating our show. I'll get to some details in a minute, but the show is kind of about the Milky Way. Can you see it behind me there? This little image here is actually one I borrowed. It's from the Grand Canyon Star Party. This year. It was last June. They do one of those every year. And, so we're going to talk to you about the Milky Way. What is that sort of cloudy path through the sky? What's it made out of? Why do we get to see it like it is? We're going to talk a little bit about how the Milky Way has been sort of attached to cultural stories and things like that over the years. And to do all of that, I have a very special guest, and I'll introduce her formally in just a little minute. But Karen Neerman is a professor in our school, and she studies this, not only the cultural side of astronomy, but she also studies some of the science behind how we know about the Milky Way. We're going to talk about that a little bit. Before I get there, let me introduce myself. I always forget to introduce myself and the rest of the team. So I'm Rick Alling. I'm the manager of community outreach at the School of Earth and Space Exploration. And we started this particular program, Virtual Night Sky, over 2 years ago. It was one part of our COVID response to keep in touch with people. But people keep joining and they keep signing up. And every other Wednesday we do this. We have some guests that don't usually attend tonight. And so I'd like to just do a big shout out for Tracy Dodwell, who's a teacher that we've been working with in the elementary school system for years. She teaches at Kokopah, and she's invited her students, because their school has also started, she's invited some of her students to join us. And so I'll tell you a little bit about how they might participate in the program tonight. Along the way, just returning from vacation is Meg Huffer. Remember, she wasn't with us 2 weeks ago. I am back. Meg is coming back from the Midwest, a big, huge car trip. I'm back from my little tour of Santa Fe and a little place outside of Pecos, New Mexico. Alicia Hyatt is with us tonight. She just is returning from Disneyland, right? Disney World. And then also students Alex Blanche and Armand Dalla are also here to help work in the background, and they'll be doing some presenting as well. So with that team that's we've been kind of using and working with over the years, let me just give you a little bit of some housekeeping stuff. We like to use closed captioning. You can turn it on or off of your own screen. You don't have to use it, but we do that. And we do record these programs and then later post them on a YouTube channel. And you can find that on our website anytime. So if there's something you like or something you want to go back and review, give us a day or two and sort of like get it up there, and you'll see, you'll be able to go back and reference it and look for it. So that's why we use the closed captioning. We do not allow chat. So if you're just dying to talk to us, and I hope you are, we do that through a different function. We use the question and answer button. And so tonight, especially, if you have a remembrance of the time you saw the Milky Way big and bright in the sky, you sort of have, you remember seeing it earlier someplace while you were traveling, and the Milky Way was really big and wonderful outside of the city lights, of course, that would be great. And then I'm also going to ask Tracy's students, if you'd like to sort of like participate, I want you to just go take when you're ready, go to the question and answer button. If you would just use your first name and the grade level you're in, and then just pose a question for us, I think that would be great. You can do that anytime along the way. We'll be doing this for about an hour, and we'll see how that works. And with that, I think we probably should get on with the show. So I'm going to ask to come to the screen with me, Dr. Karen Neerman. Karen is also part of has been part of our program for quite a little while. Karen and I guess we've known each other for about 12 years. I guess Karen runs the labs on ASU campus this year. So, and we participate in that, use the resources of the School of Earth and Space Exploration to help support the labs. So, known each other for a long time, and Karen and I also are members of an organization. Sometimes we sort of share it with you. It's called the Society for Cultural Astronomy in the American Southwest, and so she and I sort of kind of do that stuff avocationally. We're both on the board of that particular organization. So Karen, welcome, and thanks for joining us tonight. And I think this is great.
Thank you. It's great to be here.
What we were gonna. What we were going to do for this first half hour, it really is a conversation. So Karen and I are co-presenting sort of the things about the Milky Way, and I'm just going to go right to a little camera view here and see if this is still sort of set up and see if it's still working. Yep, there you go. I have control of this. I hope everybody can see the Earth in front of you. Do you want to see where you live? Actually, this is actually real time. I mean, it's not real, it's a simulation, but it's presenting in real time. And you can see that about half the United States is already dark, and all the lights are coming on in those particular places all over across the country. And we're sort of just right at that shadow line. So the sun went down a little bit ago. We're in that part of night. In fact, I just reset this about 10 minutes ago, but let me do it. Watch really close. Here we go. Ready? There it is. So that's really it. And this actually, this actually sort of looks like Phoenix about right here, I think. So where we are. So it's just dark where we are. One of the reasons to start here is, first of all, I want to show the relationship in the Earth and the Milky Way. Kind of that's how we're going to get started here. But to actually see the Milky Way, to actually go out and view it in the night sky, you have to be away from city lights. And that's not only here where we are, but anywhere in the world. And so some of the questions we're going to ask you along the way is, have you ever seen it? And every once in a while, this is really fun, we take our incoming freshman class up to a place called Camp Tonazona, just outside of Payson. And we're going to do that in a couple of weeks. And we introduce them essentially to the night sky. And inevitably, there's many students, Karen, you remember this, right? There's many students up there that just have never seen the Milky Way before. And finally, right? And that's not that far away.
Right.
Payson isn't too far to go to sort of check out the Milky Way. But you do have to be, unfortunately, definitely have to be away from the city lights. So it's not really something that we just get to see all the time. So I just want to sort of start there. Let me back out a little bit. And I'm going to get just far enough away that I can start swinging around. And you can see how the Milky Way is that sort of cloudy path, just sort of floating up through the sky there, or through the sky, and the Earth is in front of it. And I'm just going to go up a little bit just to sort of show you. The Milky Way actually goes all the way around us. So from your perspective, when you go out and look at during the night sky, of course, you got a horizon. And it's sometimes straight up over the top of us, which is this time of year. That's where it is. One of the reasons why we're having the program tonight. But other times it just kind of hugs along the horizon, and sometimes it's more noticeable than other times. And so you just gotta kind of know a little bit about where to look, when to look, and you really do have to be in those dark locations to sort of do it. Karen, when's the last time you saw the Milky Way?
Oh. That's a great question.
It wasn't
when was the last
night,
time
right?
No, I live in the city here, so it's been a while since I've been out.
Before I get too far away here, I'm flying around. We're going to kind of have little chats like that as we go. I'm going to turn on the orbits of your solar system. So remember, the Earth is that blue orbit right there. You can see where the Earth is, and the sun's right there. And I think we've shown you this before. And so I just want to kind of show you that our solar system is a disk. And we are tilted about 23 degrees, right, within that disk. I think people pretty much know that. But and all the planets kind of, we look out, we call that the line of the ecliptic. When we look out, we see planets sort of along the plane of the solar system. But now I've got a little view here where you can see the plane of our solar system compared to the plane of the Milky Way. And you can see that we're tilted. We're not sort of aligned, if you want. So there's a, let me just, if you sort of imagine, there's a disk of the solar system that looks like a frisbee or pancake or record album. And then there's a disk of the Milky Way, same kind of thing. It's flat and dish shaped, but they're not aligned together. They actually sort of like are offset about that much. And if I'm just going to shoot out here, just get you out to a solar system, a Milky Way view. If I get way out here, you sort of see now, I know that was really fast, right? We just went from Earth to 100 million miles away from Earth in just a little bit there. And this is really what it looks like. And let me just sort of illustrate the shape, right? Remember, disk of the solar system, disk of the Milky Way. That little middle part is this, what we call the central bulge. Karen, so what type of galaxy is this anyway?
Yeah, so we live in a spiral galaxy, and if we want to get really technical, a barred spiral galaxy.
And that's going to be that sort of bar, that bar shape,
yeah,
in the middle, sort of stretched out and elongated.
Yep, that line shape, that line, and then that circle in the middle, that's the bulge, and then we have the spiral arms, or those blue gorgeous arms that twine around it.
Sometimes when we use this illustration, people ask afterwards, and I always try to remember to say this, that the center is not really something different, right? In this illustration, it looks like there's some sort of like giant sun thing in there, but this is just a representation. It's really just the combined light of billions and billions of stars in the center, right? And,
that's right. Yeah. So if we were to zoom in or fly in, it would just be a whole lot of stars. The same as when we look up at the night sky, right? When we look up at that Milky Way, it looks like a cloud, but if you were to look at it with a telescope or a pair of binoculars, you would resolve out all those thousands and thousands of stars that you would be looking at. So that was actually, that was actually one of the discoveries that Galileo made. We think about Galileo as, oh, he discovered craters on the moon, or the moons around Jupiter,
the moons
Saturn's
around Jupiter,
rings, right? The Galilean moons. But he also discovered that the Milky Way, that band of light in the sky, is made of thousands and thousands of stars.
In this little illustration, what I'm showing you is essentially how we're embedded in that disk. And it's kind of hard for people. I mean, you don't automatically visualize this, but if you think about a disk of stars, a high concentration along that plane, and then not very many stars above it and not many stars below it, right? And so our view of the night sky, as you can sort of see, sometimes we're looking across the disk, and that's where we see that cloud shape of kind of going over the, in fact, I'll try to put it in the right orientation so you can sort of like visualize it as we were looking before. So it actually looks like this. The plane of our galaxy is going, or the plane of our solar system is going right and left. And then we see sort of the Milky Way galaxy up above, sort of in that pretty thing. But you can sort of see from this illustration that hundreds of millions and millions and millions of stars embedded within the disk, and we're in there. That little circle represents where we are. And you can see there's the central bulge. We can see across the plane into that central bulge, and we can see kind of out towards the outskirts. And science.
If you also notice, right? So all the stars in the sky that we're seeing, right, are still in the Milky Way galaxy. They're just out of the plane, so they're not as clumped together, if you will. They're sort of scattered. So we're looking out of the plane, whereas where you see that cloudiness, you're either looking kind of toward the center or out away from the center, but along that plane. So,
and I think when we do research, when we do surveys of the total sky, when we look at other galaxies, researchers tend to look up, right, away from essentially the bulge of the galaxy, because that just obscures their view, right? And they look down, they look up, through less stars, less material to get in the way. And that's kind of how we study the universe beyond the Milky Way. How many stars in the Milky Way?
Okay. Let's see.
I'll tell you what we use. And in the planetarium, we use 200 billion.
Yeah,
but
something like that.
I've seen a range that is twice that, right? I mean, we don't really know, and you can't count to 200 billion. That's just kind of crazy. Yeah. And maybe we should also mention, we don't necessarily see the other side of the galaxy, right?
Right.
So on a model like this, we actually have to infer what the galaxy looks like on the other side. So we know we're a barred spiral. We see other barred spirals in the sky, but really, so where my little arrow is pointing over here, that's a part of the Milky Way. We just don't really get access to it. We don't see it. We sort of study closely everything around us. We know the central part of the galaxy, and then out there. All right, so I know there's a question coming.
There's so much dust in the plane of the galaxy that it's blocking that light that we could see on the other side.
Yeah, we'll be able to do that. And I know the question is going to come up. What's in the middle of the galaxy? What's like in the center part,
What is in the center? So in the center of our galaxy is a massive black hole. It is much, much bigger than the sun. So if we say our sun is and we use that unit of measurement, is 1 solar mass. So the black hole in the center of our galaxy is, what did we figure this one out to be?
I think it was 4 million times the mass of the sun. Is that what it was? I think so. 4
million times the mass of the sun. So really, really big, but still, right? It's a bit, the actual size of it is still relatively small, but there's so much mass packed into so small of an area.
And that really is the definition of a black hole, right? It is so massive, and there's so much gravitational attraction that it prevents the light from escaping. And so, and then I think researchers, correct me if I'm wrong, but we believe there's a supermassive black hole, or black holes in the center of all galaxies, right? Is that a known thing or a supposed thing?
Almost every galaxy we look at, we can see evidence for a black hole at the center, a supermassive black hole. We're still looking for some, like some of them are, really small galaxies. We're still looking for some of them, but almost all of them have a supermassive black hole at the center. So,
Then while we're still in this view, and then we're going to kind of move on to a little cultural chat here for a minute, I just want to show, this illustration shows the difference between the light parts and the dark parts. So there is dark material, dust. We can sort of think about like dust and smoke and things that you have trouble seeing through. That's embedded in the Milky Way. And then there are light parts where the stars are shining and illuminating clouds of gas beyond them. So clouds can either be sort of irradiated and illuminate when you see them, or they can be a block. They can actually be opaque and block the light from the background. And in the galaxy, we see both. I mean, that's really what gives it this texture, right? So, and then other cultures have seen this too. So I'm going to kind of stop my share for a minute, and I think Karen, you were going to do some PowerPoint.
I do. Let me go ahead and share
little festival going on over on the other side of the world right now.
That is right. So this time of year, oops, I realized there we go. We're gonna start in over in Asia, so East Asia. This time of year celebrates a festival associated with the Milky Way, and China is one of the more common places that this is celebrated. It's also celebrated in Korea, Vietnam, and Japan, among others. And in those cultures, they call the Milky Way Silver River. And I've written, here's the kanji that describes that. And so in Chinese, they pronounce it Yinhe, and in Japanese, Jinga. And I thought this was interesting too. In Japanese, the word for all galaxies is actually Jinga. So they call that after the Silver River. So, and so here we have a picture of the galaxy sort of seen, night right now. When it's dark, you go outside and you look and you see the summer triangle overhead, and the Milky Way is running through the summer triangle. And let me turn off some of the words here. And you can see here, there are 3 stars, they're labeled here, that make up the summer triangle. And you may have, if you've tuned in recently, you may have seen and heard about the summer triangle, and the stars Vega, and the star Deneb, and the star Altair. So those 3 stars. And between them runs the Milky Way here. And the story that is told about this is that there's a beautiful heavenly woman, heavenly fairy in some stories, or heavenly girl, and her name is Jinyu, and so she is represented here by the star we call Vega, and then she falls in love with a very very nice man who is a cow herder. So right, he herds the cows, and his name is Niu Lang, or he is represented by the star that we call Altair. And so, as you might imagine, a heavenly girl falling in love with a human is just, very not to be born.
It seems like we hear this story over and over again, right?
Right.
In Greek mythology and in other stories, right? It wasn't meant to be. They're not supposed to be together. Is that right?
They're not supposed to be together, and so they secretly come together, and they secretly decide that they want to be married, and so they're married, and they have 2 beautiful children together, and they are happy and in love. And also they in this phase, they kind of neglect their duties, right? They're not really herding the cows. He's not really herding cows. She's not doing her weaving, and so they come to the attention of the empress, of the heavenly goddess, and she says, oh, what have you been doing? And gets angry and separates the 2 of them, leaving the children on Earth with their father, and taking Weaving Girl back up into the sky. Well, of course, as you might imagine, they are heartbroken, all of them. They are crying, weeping, and so seeing their love and then the subsequent sorrow, she relents and decides to give them 1 day of the year. And so here's where I've kind of written out the story a little bit. But she gives them 1 day of the year where they are allowed to meet together and spend 1 day together. Here's an illustration of this from the palace in Beijing, of Weaving Girl meeting Cowherd and their 2 children, getting able to see their mother. And the day that this happens is actually called the 7th day of the lunar month, 7th day of the 7th lunar month, or the Day of Sevens. And because the lunar month actually changes relative to our months, this year that aligned on August 4th. Next year it's August 22nd. And so this celebrates the day that Junyu and Niu Lang are allowed to meet once a year. And the magpies actually fly down and form a bridge across the Silver River to be able for them to meet each other.
So in this art, whenever you see sort of little illustrations of this, you'll always see them all surrounded by these little bird figures and the magpies.
Yeah,
That's always an important part of the thing. Yeah. And then if you're counting your lunar months, you start with the Chinese New Year. And I think everybody already knows maybe the Chinese New Year moves a little bit, changes by about 10 days a year. And it starts at a new moon. And that's a gigantic celebration also in Oriental culture and Eastern cultures and their way of thinking. And but this is kind of become their Valentine's Day, right? I mean, isn't this this is sort of how, if we sort of celebrate whatever February 14th, that's when we sort of like bring flowers and candies and all that stuff. But this is theirs. This is when they do it, right?
Right. Yeah. So as you might imagine, so the celebration of this day is a celebration of love, right? The love between the 2 of them. Also, in Japan, it's also a day of celebrating starlight, also wishes. So the different cultures all have a different name for the day. So Kishi in China, Tanabata in Japan, and for Tanabata, you actually have these small rectangular pieces of paper that you write wishes on, and you stick them on a tree of bamboo. And so that is one of the celebration things. What would you like to do, and wishes for the year. And also celebrating magpies, right? The celebration of the bridge that they create. Now, right. And so also Korea, Chilseok, and Vietnam, Thought Teach is would be the name then. So all these different cultures all celebrating this particular story, even though in the different cultures and even in China, there's some variations on the exact details.
But it also represents hundreds of millions of people, right? I mean, this is not some obscure, forgotten celebration. This is happening now. People are they just come out of the womb for this. So,
right. Yeah. I mean, and they're this is right, one of the big festivals, in the summertime, and there are various places that really concentrate and celebrate this. I actually happened to be in New Zealand a few years back, and at the observatory there, they were also going to be celebrating Tanabata. So that was so even in the diaspora of East Asian people, as they move around the world, they also bring their celebrations with them.
That's excellent. Okay, I'm going to take us back to the sky view again, if you want. We wanted to just do a little science-y thing here for a moment. And so I think it's pin my screen. Somebody would do that for me. And so what I wanted to do is sort of show people sort of a little bit about how wavelengths and light works, if we can. So I might have shown you this image before. Am I actually showing up on the screen, or I guess I probably am. I'm seeing Karen, but I guess everybody else is.
I see your screen, and I see
okay.
Me,
So essentially, I just want to remind everybody sort of the science of things. This little line right through the middle of this screen here is what we call the electromagnetic spectrum. And way off on this end is very, very high energy things like gamma rays and X-rays. And way off at the other end are low frequency, long wavelength, low energy kind of things. And when we look up at the night sky, when the ancient cultures for thousands of years look at the Milky Way, our eyes only see a little bit of the spectrum, just a little bit. And also represented here is some spacecraft and some ground-based things, and you can sort of correlate them to the part of the spectrum that they see. What I wanted to do today is I just want to show you a couple little of things where we see the Milky Way in different wavelengths. And so what I've lit up here is this is an instrument that just looks for gamma rays. So this is a telescope that is used for like surveying the sky, but instead of looking at visible light, this one is looking for this really, really high energy things. And gamma rays is one of the ways we can we look out at the sky, all different directions. We can see things. If we train it on the plane of the Milky Way, then we're seeing those places that are giving up a tremendous amount of energy. Like in the center here where that little bulge is, that's kind of the center part of your Milky Way as well. And you can see the red is high energy, the white things are kind of high energy sources. And then if I look above the plane of the Milky Way again, it's much, much lower energy, lots less transmission of energy coming from the top and the bottom. Everything that we're seeing here is sort of showing that bulge in a high energy thing. And so I'll take that one off. And then this one is called H alpha. And
out in the gamma rays are actually many of them are coming from things like the death of stars. So the supernova, when a very massive star explodes, that's often what you're seeing is energy from that. So.
And you can see stars in the foreground. Those are just sort of what I'm saying, but I'm really looking at essentially the background of stars. Okay, H alpha. So tell me, this is a very particular band of light, and what does it show us? I think you do some research here, right?
Right. Yes. So I actually use this particular. We call them a spectral line. So each atom has its own fingerprint, if you will, of light from the atoms in the electron, from the electrons in the atoms. And this particular, it has one single wavelength, 65, 63 angstroms, if you want its phone number. And this is, yeah, right. And this is light that traces where young stars are forming. So stars that are less than 10 million years old. So when stars are forming and those young stars, you're going to have a population of very, very hot stars that only live, a few million years. And so that very high energy coming out lights up the hydrogen in that nebula around them, in that gas and dust that they're being born out of. Yeah,
these little nodules down here, is this going to be like a little star forming region and a bunch of little baby stars are being born at once? Is that what's happening here?
Little stellar nurseries, yes.
Sounds kind of cute.
And so I look at these regions
too far.
Yeah, I look at these regions in other galaxies, but some of what I compare what we see in those other galaxies to some regions in our Milky Way and also in our nearby galaxies.
So are some galaxies more active in star formation than other galaxies? Can you tell?
Oh, yes. So one of the best ways to get an enormous amount of star formation is to take two galaxies and smash them together. So a galaxy merger, if you've ever seen the antenna galaxies, that's one example.
And I think the James Webb spacecraft is showing us a little galaxy merger.
That's right. There's the one of Stefan's quintet where those galaxies are that group of galaxies that are all colliding together. So those galaxies, they're clouds of gas and dust, right? They're spiral arms. But when you smash them together, those big clouds of gas and dust are going to get all disrupted and smashed together. And that's what's going to form massive amounts of new stars. And so then you'll get very, very bright in this hydrogen alpha line.
I think that's great. Let's see. I think I have a couple more here. I wanted to, this is just so, this is what we call far infrared. And remember we were talking about those clouds, the gas clouds that are cold, that are opaque. Infrared can actually see through those. Since infrared's looking at heat, right? So we can actually almost like Superman X-ray eyes. We see through those clouds and we can see heat and things in the background. Is that right? Do I have that right?
Right. And also, right, those dark clouds in the visible, those are very dense places where you can get some new stars being formed. Well, new stars are going to warm up those clouds. And so those clouds are going to glow. So even though they're dark in visible light, they're actually warmer than the surrounding area because of those new little baby stars. So in far infrared, yeah.
Look how hot things are getting here. Look at that.
Yeah. And so if you were to superimpose the picture of our Milky Way that has those dark bands, they would lay right on top of those bright bands. So
okay, I get it. Okay, and then the last one I want
the James Webb Space Telescope is also
that's right. That's kind of in this wavelength.
That's one of those wavelengths. Yep.
Towards the towards the infrared. Okay, super cool. And the James Webb is going to look at a lot of things. And we're kind of interested in these deep galaxy views, but we'll look at our own. We'll look at us.
Oh yeah, we'll also we'll look at our own galaxy in fantastic detail. I
like this one because it's pretty. So this is carbon monoxide. So I think everybody sort of knows there's carbon monoxide around here, right? It's from burning things, right? And you can get poisoned by carbon monoxide if you're not careful, if you don't ventilate your campfires enough, and that kind of thing. But so why do we look at carbon monoxide in space, though? What's going on?
Right. So it turns out, carbon monoxide is what we call traces, or is related to those very dense regions where we have lots of gas and dust together. So carbon dioxide is one of the components of dust. Most of the dust is actually going to be hydrogen dust, but it turns out hydrogen, the molecule, is very difficult to detect.
Okay,
so
I get it.
Carbon monoxide is easier to detect, and so that
and since they hang out together, when we find
they hang out
we can,
together.
we can measure carbon monoxide, and we can know where. And this is molecular hydrogen, right? So this is where atoms are kind of collecting and sticking together.
Right. Yeah. So these are the densest, some of the densest of those clouds of gas and dust. So,
absolutely.
And this is also something I look in other galaxies. One thing you can do. Yeah, one thing you can do is actually compare the amount of carbon dioxide that you see to the amount of that hydrogen alpha line. And so you can say, how much are the materials for star formation? How much stuff do they have to make stars versus how many stars are they making? And then you can determine how efficient they are at making stars. Are they converting all of their materials into stars fast or slow? Or that's a lot of what I do.
That is super cool. And I'm always amazed that I can find somebody that knows as much about the Kishi Festival as molecular hydrogen in galaxies. So, and then actually tell everybody about your necklace before, and I'm going to just change.
Okay, yes.
Kind of like,
so this is actually my wedding necklace, and it was made by a jeweler named Delight Edgel, who was out of Benson, Arizona. And it is actually the summer triangle. So the three constellations of the summer triangle. And the first one that she made was actually for a couple that were very influenced by, had Chinese heritage. And so were influenced by the story of Weaver Girl and Cowherd. And so they wanted a wedding necklace that incorporated those constellations. And then she asked their permission and offered it for general sale. And I said, I've got to have one too for my wedding. Absolutely. So this is my wedding necklace.
Oh, that's really super cool. Yeah, see how that works? Well, good. I'm going to stop this. I'm going to sort of like go back to my view, and I'm going to invite our team in the background to kind of bring some questions forward. And we have a poll for you guys. So this is you interact with us. We're going to present to you some poll questions just to see if you've been listening and how that works. So I'm going to turn it over. Who's coming on? Is that Alex? Alicia?
I'm going to do the poll question. Hello.
Wait, before you start. So Disneyland and what? Disney World?
No, just Disneyland. Yeah.
And what prompted you? You've been there before, right?
10 years ago, and my little brother, he's not so little, my little brother wanted to go, and I was like, yes, anytime he wants to spend with me, I'll take. So
okay. No, that was good. Well, I'm glad you could sneak that in before things get like really crazy.
Yes.
Good. And welcome back. And then what are we doing here? What's up?
Yes, poll questions have already launched. The first one is, have you seen the Milky Way? And the second one is, how massive is the black hole in the center of our galaxy? So go ahead and answer those two questions. And I think Alex might come on and take some audience questions.
That'd be great. I'd love to hear.
I sure can.
Can I remind you, did you get any of those students to respond, Alex?
We've had a lot of students asking questions in chat. We've had a lot of black hole questions, obviously. But we have a couple questions. None necessarily mentioning grade and age, but we do have a question from Jesse that's more related to the program that's been going in the background. But he was wondering, is the program that you're using available to the public?
Oh, good question. And sorry, no. So this just the short story is this particular program was developed originally by, the data was developed, and the way to look at it was developed by the Museum of Natural History in New York and the Hayden Planetarium. And the company that we use to sort of outfit our Marston Exploration Theater with this is called Skyscan. So the program that I'm sort of using is called Digital Sky, or DS2, I guess is the version we're using. And it really is not a sort of a commercially available thing, but there are. And so I think maybe I'll show a demo on this show a little bit later about another program that I'm kind of excited about. And it's a little hard to use, but if you're a geek and you want to try this and you've got some good computing power, there's a thing called Open Space, which operates very close and very similarly. And as it implies, it's an open source program that also is developed in New York by the same observatory, but that's their new version.
And I know we've had a lot of other programs on the show as well that have been publicly available that we do mention in Showcase. I know Stellarium is one of those.
And
We also
I'm going to be showing, after the break here, I'm going to actually be showing some people a little planetarium called Sky Safari, and I'll show you that in a minute.
Perfect. Yeah, and I think let's see. It was less of a question, but when you were talking about the electromagnetic spectrum and viewing these galaxies, we did have Tracy mentioned that a lot of middle school kids are learning about the electromagnetic spectrum right now, so starting them early.
Good.
Yeah.
It's great. No, I mean, I think I don't know. Karen agrees, but the electromagnetic spectrum is really, that's the secret sauce for our ability to discover everything, right? Because as she said, every atom has a signature. Every atom behaves the same way, and everybody delivers their energy in a very, very specific wavelength or wavelengths along that spectrum. And so we just learn to look in the spectrum. We just learn to turn our eyes on, technically, right? It's sort of through cameras and technology and that kind of stuff. We can tell a tremendous amount about the sky, right? Am I saying that right, Karen? You're the
definitely.
scientist.
I mean, my one of the things that's been amazing to me is to be able to get to work with all the different flavors of light, all the different parts of the electromagnetic spectrum. So not just going out and doing visual light, but also infrared and millimeter and radio and ultraviolet, and all of those different wavelengths give you different information about an object. And so then you can put that information together to tell an even bigger story about what's happening in that object.
Then the other thing the students are going to learn, if they haven't already, is this thing called redshift, right? Everybody, I think people know that, right? There's a thing called redshift. You hear about it all the time. But because we know where atoms are supposed to be on the spectrum, and then we see things in wavelengths that have shifted a little bit, either one way or the other way, right? Because the spectrum, that tells us if those things are moving away from us or moving towards us. And so now not only are we identifying the atom, but we're giving it some dynamics, right? Is it moving away? Is it part of an expansion? Is it coming towards us? Is it part of contraction? That's the secret sauce that does everything.
Right. So, yeah. So then you can get the motion piece on top of it. That's really cool.
I think that's absolutely amazing.
I love the electromagnetic spectrum. My freshman year project was just about how much stuff you can use with it. And I think we don't really have any other questions right now, so I'll kind of disappear into the background and try and find some more.
Can still ask. And Alicia, how did we do on the poll? So it looks like people were listening when they said 4 million solar masses. Could you tell that we were like priming you to like get you to know that answer?
Yeah, I was worried, but I'm super excited to hear that 3/4 of us have seen the Milky Way. That's wonderful. And for that last quarter, I encourage you to get out there on a clear night or go somewhere where it is clear. And then, yeah, our second question, as Rick mentioned, most of us, 70% of us got that right. So great job. And I will turn the program back over to our two hostesses with the mostesses.
Thank you. I appreciate it. Thank you, Alicia. And yeah, I don't know if I look at the, have you seen the Milky Way? Is that the glass 3/4 full or the glass 1/4 empty? I guess.
I think it's great that people have seen it. Yeah.
It's also kind of a sign of the times, I think, right? And we talk a lot on this particular program about dark skies, dark sky communities, the idea to preserve dark sky. And you can see in the background right up at the Grand Canyon, the reason people go to a Grand Canyon and have their star parties up there is because it's a lightless sky, or as near as it can be. And many of the national parks have adopted the dark sky ordinances and things. So I'm pretty excited about that. Hey, I wanted to sort of show everybody this a little bit. And if you've seen this before, what's happening on the screen here is this is a program called Sky Safari Pro, and it shows you where the sky or stars are. The way I have it set up now is everything within that green circle is visible right now if you got a dark enough sky. And you can see from this particular image, can you see this sort of the Milky Way band going from the right to the left? And before I get to the stars part, I just wanted to remind everybody that there are planets up as well. And Saturn is available in your night sky right now. It sort of has come around, if you want. These were all morning objects several months ago. Now they're starting to become evening objects. And we'll be talking a lot more about this later, but the big, huge granddaddy of them all is going to start becoming available to us very soon. In fact, right now you can see it. If you stay up until about 10:30, you'll see Jupiter in the eastern part of the sky. As the months tick away, Jupiter will become more and more prominent earlier and earlier in the evening until it and Saturn and Mars are all up above us in the first part of November. So it'll be kind of fun to look forward to. But anyway, back to what we were talking about. Here's another reminder. I'm going to just do a little screenshot so I can draw here. But these are those three stars we were talking about. That's the Kichi Festival. That's Vega up at the top over here. That's Deneb, is the tail of the swan over here, and Altair, which is the eagle constellation over there. And all three of those. And then as you can see here, the sort of the band of the Milky Way kind of goes through them like that. I'm just going to erase that for a second, because if you can't see the Milky Way, you can see where it is. So I'm just going to get a little bit more detail here on the swan. So first of all, some people call this, there's an asterism here called the Northern Cross. And so this was Deneb again. That's the very bright star, DNB. That's the very bright star that sort of forms a cross. And then if you extend these out a little bit further, there's some dimmer stars over here, you start to sort of take on the shape of a swan. And so I'm just going to try to do a little swan flying here if I can. So I'm just going to kind of put some wings to this thing. I think this is a beautiful constellation, and to see it in a dark sky and see it sort of, just for its beauty and its grace, I can see why they call this a swan. And its tail is back in this particular direction. Deneb literally translates tail of the swan. And then if you know, swans have these beautiful, long, graceful necks that sort of go out in this particular direction and kind of take it all the way out here. I'm going to give it a beak and a couple of eyeballs. And so there's a swan. But notice that the tail and all the way, the elongation of the neck all the way through follows exactly the Milky Way galaxy. So it's just sort of like, so if you have trouble seeing it, you never have, you can see this Northern Cross. It's easy to find. If you look a little bit harder, you can define that cross as a swan flying through the sky. And if you follow the neck of that swan all the way down, you're sort of you're following the Milky Way. And then remember that the cow herd is up here and the princess is down here, separated by that river. It's on one day a year. Sorry you missed it. It was August the 4th. The magpies come and fill that up. So you've got a little bit of a Greek mythology laid on top of Chinese mythology. And but that's really what the sky is all about. It belongs to everybody, all cultures across all time. And I think that's really just a beautiful way to think about it. All right, I am checking the time here because we do have a couple of things to do, but I wanted to show you one other thing before we go. Down in this part of the sky, so now I'm looking right into the south. And there are two constellations here I want to show you. This one's called the Scorpion. Turn on my pen, not my eraser. And it's sort of, you can sort of see it's this long line of stars that goes like this, all the way around here, up this way, and then there's the little stinger of the tail. So if you want, you can imagine the body of the scorpion here, the claws of the scorpion going out this way. And this star right here is called Antares. It's the heart of the scorpion. I'll give him sort of 8 legs because he's an arachnid. And so this is really Scorpio the Scorpion. And it's really easy to find. And look, notice the tail crosses the Milky Way and kind of wraps around a little bit. The other really cool thing over here is Sagittarius. And Sagittarius can be found by sort of identifying this little thing that looks like a teapot. So here's a little handle for the teapot over on this side. Here's the spout of the teapot sitting on this side, and you can sort of see that. It's actually easy to find. This is actually, if it wasn't cloudy tonight, you go up a little bit, it's easy, right?
Yep, and if you the teapot is about to pour into the Milky Way. That's one of
it does, yeah. So if you can sort of imagine, I sort of see steam coming out of the little spout right here, or if you were to sort of like empty it, right, you're sort of stuff will flow out over here. If you sort of just kind of come out from the top there to about right here, I'm saying about is pretty much the general area right here. This right here is the center of the galaxy. Remember we saw it. Remember we saw that big central bulge. Remember we saw in various wavelengths of light all that energy coming out of the center. Remember we talked about a supermassive black hole right in the middle. That's it. That's where it is. And you can't actually see the stars and the brightness at the center of the galaxy. It doesn't identify itself as a low point, but now you know where it is. Now you know how to find it. And so think of that teapot and think about sort of like this stuff sort of flowing out. And there you go, the very center of the Milky Way galaxy. All right, sound good, everybody? All right, we're still entertaining some questions if you have some, but I'm going to turn the microphone over now. We're going to have to get a little update, a couple launches. One happened about a week ago, and we got an update on that. And one is going to happen next Monday, we hope. And we'll get a little update on that one. So I think we're going to start with Armand. No, we lost Armand.
Okay.
Oh, there he is.
All right, sorry for a second. Let me just get it set up and available to share my screen. But yeah, a couple of weeks ago, on the 4th of August, the Korean Pathfinder lunar orbiter launched from Cape Canaveral, Florida, aboard the SpaceX Falcon 9 rocket. And on board the spacecraft are 6 science instruments, and one of them is called Shadowcam. And that was developed by researchers here at ASU, part of the Lunar Reconnaissance Orbiter camera team.
This is the first time I've seen the picture. There they are.
Yeah, there they are. We had a little launch party, a launch watch party at the theater as well. That's the video you're seeing right now. But the goal of Shadowcam is to look deep into permanently shadowed regions on the moon itself. And we're doing this to find out about how much hydrogen in the form of water ice is there in those permanently shadows deep in the moon. And we're actually going to be looking at it through a very, very sensitive camera. It's about 200 times more sensitive than the latest camera, the narrow angle camera aboard the Lunar Reconnaissance Orbiter camera. And these are some more photos from the launch party that we did here at the theater. But we had a panel of great experts, part of the LRO team as well. And it's a great experience. And I'll be here sitting, waiting on the moon, waiting for Shadowcam to come. But I'm gonna turn it over to Alicia now for some updates on LunaMap.
So just before Alicia starts, and I wanted to sort of like, well, we'll bring Kim to the table too, but I just want to kind of give an update. I checked with the team even today, and after launch, of course, you want to know that your instrument works. It makes it through the shake, gets out of the atmosphere, gets up into space. And indeed, they know the camera works. They've tested it. They don't have any images in light. We're doing it in dark space right now. And they know it works, and we're getting telemetry, which means that it's sending signals. They're talking to the camera the whole time. That's exactly what we expect to happen. And so that part of the mission so far is a success. And we're going to actually have guests from LROC on 1 month from tonight, on September the 21st. We'll get a bigger presentation, and by that time we'll be able to talk to us about their mission, how this thing is going to start, when we actually get to see some science and that kind of stuff. So very good. All right, and then I think it's Kim. Kim, are you? You don't look like you're here. You're not in Phoenix anymore, are you?
I'm not. I am not in Arizona. I am actually in Florida, getting ready for the Artemis 1 launch. And we are going to be exhibiting tomorrow over at the Kennedy Space Center Visitor Center. I think Alex has some pictures of what it looks like on the inside. For this,
I'd like to see.
we're going to be So that's what it looks like inside. And that's kind of empty, and that's what our table will look like. And I'll be standing behind there with Craig.
Okay.
This weekend. When I left, they were still assembling everything. There was like crates and boxes and all kinds of stuff being assembled for this exhibit that's going to start tomorrow through day of launch.
So should we say, "Oh, good for you, yippee you get to go to Florida," or is it all fun and games? Or?
It's all work. So
Okay.
and I'll be able to catch a launch while I'm here. But Craig Hargrove will be joining me on Saturday.
And Craig is the principal investigator. He's kind of somebody that has built an instrument kind of similar to the way we're talking about Shadowcam. There's an instrument called Luna Map and Luna HMAP, and he's the researcher, and he's right here at ASU. In fact, we built that little device here on campus, and now it's in Florida and it's ready to launch.
Yes.
So what do we expect, and how can people watch it, or can we watch it?
Yeah, you can watch it. There's several ways. You can tune into NASA Live. If you're in the local Tempe area, you can come down to the Marston Theater at 5 a.m.
5 a.m. We'll be there.
The team.
Yeehaw!
Yeah.
Wow, this is fun.
The launch time is scheduled. It's a 2-hour window that begins at 8:33 Florida time or East Coast time, and so that's 5:33 for folks on the West Coast in Arizona.
Okay.
So we're fingers crossed that it's going to go on the 29th. And if not, the next attempt will be September 2nd, but we're really hoping for a August 29th launch. And there is a way to register on NASA has an Eventbrite. I'll put it in the chat here. NASA has an Eventbrite registration so that you can keep up to date with all the things that are happening with the launch, including if it gets postponed for some reason.
Right.
And then you'll get notified like that. And Artemis 1 did put out a new video today. It's about 4 minutes long, so I don't know if we have enough time to play it tonight, but they did just show like an overview of the mission. And so we're going back to the moon, and Luna Map will be the CubeSat that's going to go look for water. So we're excited for that.
And I think we should just mention big overview. The mission, the spacecraft is called Artemis 1. Artemis 1 is a huge project. It's a very, very large spacecraft, and it's organized with a manned capsule, yet this particular launch, there's no men, right? So there's the Orion capsule. It's going to take astronauts to space. This particular is the first one. It's a test launch to get it out of Earth, off to the moon, do some testing, but it's not taking any astronauts with it now. And so that particular thing is our ride. We have what's called, we have a little spacecraft about the size of a suitcase that is in what they call the secondary payload. And so we're hitching a ride. We're going to get up into space, and then we are one of 10 secondary payloads, and the rocket will just start spitting them out. We have these little drop-off points.
They call them bus stops.
Bus stops.
We have 3 bus stops. And we are on bus stop 2, and that will happen in about 5.5 hours after launch. So Orion is a different mission within this whole Artemis mission. So Orion will drop all these CubeSats off. It will go up, and then it will come back. And so that's what they're testing to make sure, so that when they're dropping off humans, astronauts, and
because Artemis 2 is going to have people on it, right? That's an astronaut mission, if I remember.
Yeah. So very exciting stuff.
So we're actually watching for 2 things. First of all, we're going to watch the launch, right? That'll be exciting. This is a big spacecraft. It's way bigger than the one you just saw, the Falcon 9 that took our Shadowcam. And so launch has to be successful. It has to get up. It has to get going in the right direction. And then 5.5 hours later, we're going to actually get news that we have successfully deployed. Do I have that right? So Monday's a big day for us. And then
Yeah.
everybody that has been following the news knows there's weather everywhere. I mean, this has been a big month. And for us, flooding in Dallas a couple of days ago,
Mhm.
Mississippi's flooded. And so they
And it's
schedule
hurricane
these.
season.
It's hurricane.
Hurricane
So
season.
they schedule these launches. We're sort of focused on this Monday morning at 5:30, but they could have to delay or have to call the launch because of weather, and that it's just one of those things, and we can't.
Yeah.
Have it.
So
And then
no lightning within 2 miles and no winds over 40 knots. I'm not a nautical person, so that must be pretty windy though.
Yeah. Yeah. All right. And then
Um,
and then we won't let Kim come home again until she gets that rocket in the air. So you could
Yeah,
be there
so
for a while.
we want it to go on Monday because I want to come home. So.
Okay, I get it.
But yeah, and then the other part of that mission is that Orion needs to return to Earth. So that's the other part of the mission, is that that capsule will come back. So that's what they're also testing. So lots of things happening on this mission.
Right.
Lots of things.
Lots to look at, and go ASU, go Sun Devils. I mean,
Yes,
go
Luna Map.
We have something in this game. We got to get
Yeah.
that Luna Map up there, and we'll be giving you an update next week. And
Right.
we're at the end of our hour. So I'm going to just
Yes.
kind of wrap up real quick. Kim is going to send everybody that participated tonight a little email if you registered. And in that email, we usually include some resources, some things that sort of reinforce some of the things we talked about, some of the mission things that you can follow on your own. And so look for that. This launch we're talking about, hopefully, will happen between now and our next meetings, 2 weeks from now. We'll definitely be giving you an update on this. And hopefully we're telling you it was successful, it got up, it worked, and all that stuff. We'll give you an update. And then remember, a month from now, we're actually getting a much bigger sort of little science picture from the Shadowcam, the one that launched last week, or a week and a half ago. And so please keep tuning in. Thank you. I thank everybody on the panel, everybody that helped tonight, Armand and Alex, Alicia, Kim, Meg. Welcome back, Meg, and Karen especially. It's just so great to have you on, and thank you just very much for sharing a little bit of your science, a little bit of your insight into how the Milky Way works, both culturally and scientifically. And I think that's great. So keep tuning in. We'll see everybody in about 2 weeks. Thank you.